Welcome back to the deep dive. Today, we are doing something a little bit different, and honestly, I'm really excited about it.
Yeah, it's a fun one.
It is. Usually, we take a stack of dense academic articles or maybe like a really heavy nonfiction book that's been on the bestseller list, and we tear it apart to get to the core insights. We try to save you time, but today, we are going back to basics. And I mean, really, really basic.
We are, but sometimes the most basic things are the ones we understand the least.
Right.
We think we know them because we see them every single day.
Oh.
We're looking at the fundamental physics of light, shadows, and reflections.
It sounds so simple on the surface. I mean, we all know what light is, or at least we think we do. You flip a switch, the room gets bright, you walk outside, the sun casts a shadow on the sidewalk.
Exactly.
It's intuitive. It's basically the water we swim in every single day. But the document we're looking at today is unique. It's Chapter 11 from a standard classic science curriculum.
Yeah.
But it's not just a clean, pristine PDF.
No, it is certainly not clean.
It is heavily annotated. It's covered in these totally unique handwritten style marginalia, little drawings, and personal notes from a student named Aram.
I honestly love this concept. It adds such a personal human layer to the physics.
Yeah.
You're reading the hard science, right?
Yeah.
The definitions, the laws of propagation, but you're seeing it through the eyes of someone discovering it for the very first time.
It really grounds it.
It does. It grounds the abstract concepts in real, genuine curiosity.
I've been calling it the Aram factor.
Yeah.
Right at the top of the first page, there's this note that just says, "I am Aram," with a big smiley face.
The big capital D smiley face.
Yes. And throughout the text, he acts as this proxy for the curious learner. Like, he pops in with side notes about the speed of light. He gives these very serious warnings about eye safety.
Which we will definitely get to.
Oh, we have to, because they're hilarious but also totally accurate. And he shares his own personal experiences with eclipses, too.
It reminds you that science isn't just dry facts on a page. It's an experience. It's something you do. And that's our mission for today.
Right.
We want to take this foundational material, the exact stuff Aram is learning, and unpack it. We want to elevate it to explore the profound implications of how we actually perceive reality.
We're going to talk about the invisible energy that allows us to see, figure out why a shadow isn't just a dark patch on the ground, and really explore the cosmic geometry that creates eclipses.
So let's jump right in. The text starts with a bit of a paradox, something that actually stopped me in my tracks.
Same here. It made me rethink how I describe vision entirely. It hooks you with this concept of invisible light.
It's a great hook. It touches on this idea that light itself is, well, invisible.
Which sounds like a total contradiction. It sounds wrong. How can light be invisible?
Right.
The whole point of light is that it lets us see things. If I turn on a flashlight, I feel like I see the light. If I look up at the sun, I see light. So what is the text getting at here?
This is a concept that trips up a lot of adults, not just sixth graders like Aram. The text makes a crucial distinction right off the bat. Light is a form of energy. Specifically, it's electromagnetic radiation.
Okay.
But we don't actually see the photons themselves as they travel through space. Not unless they interact with something.
Okay, I want to really unpack this because it breaks my brain a little bit. Let's use an analogy.
Right.
Say I'm standing in a room that is perfectly dark. I mean, pitch black. And it's vacuum sealed, no air, no dust, just pure empty space.
Okay, a perfect vacuum.
Yeah. And I shine a powerful flashlight across that room. If I look at that beam from the side, what do I see?
You wouldn't see the beam at all.
Nothing.
Nothing. You would see the source, the glowing filament of the flashlight in your hand.
Right.
And you would see the illuminated spot on the wall where the light hits. But the space in between, pitch
Well,
black.
That is wild to visualize. I feel like in every sci-fi movie, you see the laser beam cutting through space.
Yeah, that's just movie physics. In reality, light is the messenger. It carries information.
Yeah.
Until that energy physically enters your eye, you don't detect it. Light has to strike your retina for your brain to register it.
So if it's just passing by me?
If the light is traveling across your field of vision, from left to right, none of it is actually entering your eye. Therefore, you can't see it.
But in a normal room, like if I'm in a dusty attic or standing on a misty street at night, I do see the beam.
Ah, but think about why. In a dusty room, the light is hitting those little dust particles. Those particles are acting like tiny moons.
Oh, wow.
They act like tiny mirrors, directing some of that energy sideways off the main path and into your eye. That's the only reason you know the beam is there. You aren't seeing the light beam itself. You are seeing the illuminated dust.
So Arum's text is right. Light is this invisible energy that causes the sensation of vision. It's only when it bounces off an object and hits our retina that our brain processes it and says, oh, there's a table there, or there's a dust mote there.
Precisely. Light is the delivery truck. You don't know the package has arrived until it knocks on your door, or in this case, until it hits the back of your eye.
The text places this visible light in the broader context of the electromagnetic spectrum. It mentions that our everyday devices, mobile phones, microwave ovens, remote controls, they all function using similar types of radiation.
Right. Arum's notes list them out in the margins. Radio waves, microwaves, infrared, X-rays.
But we can't see the Wi-Fi signal floating through the living room. We can't see the microwaves heating up our leftovers. Why is that? Why do we see the light from the bulb, but not the light from the router?
It's purely biological.
Okay.
Physically, a radio wave and a ray of visible red light are the exact same thing. They are both oscillating electromagnetic fields. The only difference is the wavelength, the frequency.
Okay.
Our eyes are biological instruments tuned to a very specific, very narrow band of frequencies. We call that band visible light.
So it's kind of like a radio tuner.
Exactly like that. Your eyes are tuned to 101.5 FM, but the Wi-Fi is broadcasting on 88.9 FM.
And so we just miss it entirely.
The signal is there, loud and clear, but your receiver just isn't built to pick it up. If our eyes were tuned differently, say like a radio antenna, we might see the radio waves coming from a cell tower. The world would look incredibly chaotic.
That's a trippy thought. We are just walking through this soup of invisible radiation constantly. GPS signals, LTE, radio, even background radiation from the Big Bang.
Yep.
But we only perceive this tiny, tiny slice of the pie.
We are blind to 99% of the universe's energy. We just happen to have sensors for the part that bounces nicely off solid objects and happens to come from our sun.
The text moves on to explain how this energy is created, using the example of an electric bulb. It talks about the transformation of energy.
This is a key concept in physics, the conservation of energy. You can't create energy from nothing. You can only change it from one form to another.
The text says, when we light an electric bulb, the filament first gives out heat. It becomes dull red. Then as it gets hotter, it gives reddish light. And finally, it becomes hot enough to emit white light.
It's a classic progression. You start with electrical energy flowing into the filament. The physical resistance in the wire converts that electricity into heat energy. The atoms in the metal start vibrating like crazy.
And that's incandescence.
That's incandescence. You pump enough energy into something, it gets excited and starts shedding that energy as photons, as light.
So light, in this specific case, is just a byproduct of heat.
In the case of incandescent bulbs and stars, yes. It's a transformation from electrical energy to heat energy to light energy. The heat comes first. You essentially had to pay the thermal tax before you get the light.
And speaking of that energy traveling, Arum has a very specific, really enthusiastic note in the margin here about the speed of light.
I love this note.
He wrote, nothing in the universe can travel faster than, or even as fast as light.
Arum is spot on. He's identified the ultimate cosmic speed limit. 3 times 10 to the 8th meters per second in a vacuum.
300 million meters per second. That number is just, it's hard to wrap your head around. It's too big. It doesn't mean anything to my brain.
It is abstract. Let's put it in perspective for you. In the time it takes you to snap your fingers, so maybe half a second light could travel around the equator of the Earth 7 times.
Okay, that helps. 7 times around the world in a snap. That's essentially instant. For all intents and purposes, for us humans down here on Earth, light is instant. When I turn on the lamp, the room lights up immediately.
For us on Earth, effectively, yes. But here's where it gets really interesting, and Arum notes this too. Even at that unimaginable speed, space is so incredibly vast that it takes time for sunlight to actually get here.
The notes say about 8 minutes and 32 seconds.
That's right. The sun is roughly 93 million miles away. Even at 300,000 kilometers per second, it takes over 8 minutes to cross that void.
That blows my mind every single time I think about it. When we look at the sun, which, by the way, Arum warns us later, do not look directly at the sun, but when we see sunlight hitting the grass in our backyard, we aren't seeing the sun as it is right now.
Wow.
We are seeing it as it was 8 minutes ago.
It's a literal form of time travel. Looking out into the universe is looking back in time. If the sun were to suddenly vanish, just disappear from the sky completely, we wouldn't know about it for 8 minutes and 32 seconds.
We just go about our day.
We'd still see it shining. We'd still feel its gravity holding us in orbit. We'd be orbiting a ghost for over 8 minutes.
That is a deeply unsettling thought. We basically live in the past.
We do. And the further you look, the further back you see. When you look at the stars at night, you're seeing light that left them hundreds or even thousands of years ago. Some of those stars might have burned out by now, but their ghost light is still traveling to us.
You are looking at a history book written in the sky.
Beautifully put, yes.
It really proves the point that light travels. It's not magic. It's a physical thing moving through space. It has a speed. It has a journey.
And that distinction about the vacuum is really important. The text notes that sound needs a medium. Air, water, something physical to vibrate. That's why Aram notes, I cannot hear a bell ringing in a vacuum.
Right. No air, no sound. If you scream in space, nobody hears you.
Exactly. But light doesn't care. It travels perfectly fine through the nothingness of space. In fact, it travels best through a vacuum because there's nothing to slow it down or scatter it.
Which is incredibly lucky for us, because otherwise the space between the sun and Earth would act like a giant soundproof wall blocking the light, and Earth would just be a frozen dark rock.
We certainly wouldn't be here to talk about it.
Let's move to segment 2, because the text shifts from the physics of light travel to the biology and the true utility of it, the vital importance of light.
This is where we bridge physics and biology. The text makes a strong, unequivocal claim here. Light is essential for the existence of life.
It walks through the chain reaction. It starts with warmth, which creates conditions conducive to life. But the really big one is photosynthesis.
It's the engine of the entire biosphere. Green plants are essentially biological solar panels. They take that light energy and convert it into chemical energy food. They literally build themselves out of air and light.
The text lays out this kind of doomsday scenario. It asks you to imagine a world without sunlight. And it's not just, oh, it's dark outside.
No, it's a total systemic collapse.
Yeah.
No light means no photosynthesis. If photosynthesis stops, most plant species cease to exist. They starve to death.
And if the plants die?
The food chain collapses immediately. The herbivores, the animals that eat plants, they die out. Then the carnivores, the animals that eat the herbivores, they die out. Humans, who rely on both crops and livestock, would be in serious terminal trouble.
And don't forget the oxygen part. The text mentions that photosynthesis produces oxygen as a byproduct.
Right. It's not just food. The plants are actively scrubbing the air and giving us oxygen. Without light, the supply of oxygen in the atmosphere isn't being replenished. Eventually, it would suffocate. So lack of light leads to starvation and asphyxiation.
It really highlights how fragile our existence actually is. We are entirely dependent on that steady stream of photons raining down from 93 million miles away.
We owe everything to it.
And there's an economic angle the text touches on, which I thought was really interesting for a 6th grade level text. It mentions that without natural light, our dependence on fossil fuels would massively increase.
That's a really smart connection. If we didn't have the sun to light our days, we'd have to burn fuel to generate electricity for artificial light 24/7. We'd deplete our energy reserves so much faster. Natural light is basically free energy infrastructure that we totally take for granted.
Now let's talk about color. Because the text asks, what is the color of light? And the answer isn't just white.
Well, it appears white to us, but as the text explains, natural light is a composition. It's a cocktail of colors.
I love the example they use here about green grass. It explains absorption versus reflection. Why is grass green? It's not because the grass contains some sort of green energy inside it.
No, it's about rejection. This is actually a very poetic way to look at it. When white light, which contains red, orange, yellow, green, blue, indigo, violet. When all of that hits the grass is chemically designed to absorb the red, the blue, the yellow. It eats those wavelengths.
Okay.
But it rejects the green. It reflects the green light back away from it.
So when I look at a beautiful green lawn, I'm essentially seeing the exact color that the grass didn't want.
Exactly. The color of an object is just the color of the light it reflects. A red apple is absorbing every single color in the rainbow except red. It's throwing the red back at you.
This leads to a weird hypothetical then. If I took a red apple into a room that was lit only by a pure blue light, no red wavelengths at all, what would happen?
It would look black.
Black!
Pitch black.
Because there's no red light for it to reflect.
Precisely. It absorbs the blue light because it loves absorbing non-red colors. And since there is zero red light in the room for it to reflect, it sends absolutely nothing back to your eye. It appears as a shadow of itself.
That is so cool. It really makes you realize that color isn't inherent to the physical object itself. It's an interaction. It's a dance between the light source and the material.
It's all perception based on reflected energy. If you change the light, you fundamentally change the color.
Moving on to the actual sources of this light, the text classifies them into 2 big buckets. luminous and non-luminous.
This is a fundamental binary in optics. Luminous objects are the producers. They are the sources. The sun, stars, a candle flame, a torch. They actively generate photons. They are the origin point.
And non-luminous objects are the consumers, or rather, the reflectors.
Right. The moon, the earth, a table, a book, a chair. They do not make their own light. They only become visible when light from a luminous source hits them.
The text explicitly clarifies the moon here, and I feel like this is a really common misconception for kids, and maybe some adults too. The moon looks like it's glowing. It looks like a giant light bulb in the night sky.
It really does. But it's a cold, dead rock. It's a mirror. And actually, it's a pretty poor mirror at that. The moon is made of dark, gray dust and rock. It only reflects about 12% of the sunlight that hits it. It's actually quite dark, almost like the color of worn asphalt.
Wait, the moon is the color of asphalt?
Essentially, yes.
Yeah.
But against the absolute pitch blackness of space, that reflected sunlight looks brilliant to us just because of the extreme contrast.
So if you magically turned off the sun, the moon would go dark instantly.
Instantly. Well, with that 8-minute delay for the light to stop reaching it, plus the travel time from the moon back to Earth, which is about 1.3 seconds. But yes, it has no inner light. It's strictly a reflector.
Now, within the luminous category, the things that do make light, the text breaks it down further into hot and cold sources. We talked about the hot ones, the incandescent bulb, the sun, but the cold sources are fascinating.
Bioluminescence. This is one of nature's absolute coolest tricks.
The text lists fireflies, glowworms, jellyfish, certain types of algae.
Right. Think about the engineering problem here. If a firefly had to get as hot as a light bulb filament to glow, it would incinerate itself instantly. It would be a fried fly.
A fried fly, nice.
So nature had to evolve a different way. It's a chemical reaction. The text explains that they convert chemical energy directly into light energy. The key here is efficiency.
How so?
Well, in an old-school light bulb, almost 90% of the energy is wasted as heat. You could burn your hand on it. In a firefly, almost 100% of the energy becomes light. It produces very little heat, hence the term cold light.
So fireflies were way ahead of the curve on energy efficiency.
Millions of years ahead. We're only just catching up with LEDs, which essentially mimic that cold light concept, producing light without relying on massive amounts of waste heat.
Okay, let's get into the geometry of it all. Segment 3. The text introduces a phrase that sounds very serious. Rectilinear propagation.
It's a mouthful, isn't it? It sounds like something from a complex legal contract. But it's a very simple concept. It's just a fancy way of saying light travels in a straight line.
Arum's text has a couple of activities to prove this. One involves a rubber pipe and a candle.
Simple but highly effective. You place a lighted candle on a table. You hold a straight rubber pipe to your eye and look through it. You see the flame.
Then you bend the pipe.
And the light is gone.
Because light doesn't drift, it doesn't meander around corners like smoke.
Right. Smoke would waft through the bent pipe and eventually come out the other end. Light shoots straight like a bullet. If it hits the inner wall of the bent pipe, it stops or gets absorbed. It absolutely won't curve around the bend to reach your eye.
There's another experiment described with 3 cardboards. You punch a pinhole in the exact center of 3 separate sheets and line them up perfectly on a table. You place a candle at one end, you look through the other end. You can see the candle through all 3 holes.
Because the holes are perfectly aligned in a straight line.
But if you shift one of the middle cardboards, just a tiny bit,
Darkness. The path is broken. This linear nature of light is the absolute foundation of all geometric optics.
Yeah.
It's why we can aim things like lasers or flashlights. It's why shadows have distinct shapes that perfectly match the object blocking the light.
What if it didn't work that way? Like if light curved around objects like water flowing around a rock in a stream, the world would look very, very different.
It would. Shadows wouldn't really exist in the way we know them. If I stood in front of a bright light, the light would just wrap around my body and illuminate the wall directly behind me. Everything would be illuminated from all sides all the time. It would be a shadowless, depthless world.
That is bizarre to imagine. A world with no shadows.
It would be very disorienting.
Yeah.
We rely on shadows for depth perception much more than we realize.
Speaking of rays and beams, the text defines these specific terms to help us visualize this travel. A ray is the path represented by a line with an arrowhead. A beam is a group of rays.
Right. And you have 3 types of beams mentioned. Divergent, which are rays spreading out from a small source, like a torch or a car headlight. Parallel, which are rays moving side by side, like sunlight coming from infinity. And convergent, which are rays meeting at a common point.
Like when you use a magnifying glass to burn a leaf on the sidewalk.
Exactly. You are taking parallel rays from the sun and forcing them to converge onto a single, incredibly hot point.
Now, this straight line travel leads us to materials. Why can we see through some things and not others? The text categorizes matter into transparent, translucent, and opaque.
This is all about how different materials interact with those traveling rays.
The text asks, why do we use glass for windows?
To let the light pass completely. That's transparency. The molecular structure of glass is such that it allows the visible light waves to pass straight through without being absorbed or significantly scattered. It's like an open door for photons.
But then we also use heavy curtains.
Because sometimes we want to block that light. Opaque materials, wood, stone, thick fabric walls, they are the wall. They either absorb the light, turning it into heat, or they reflect it back. None gets through.
And then there's that middle ground, translucent, frosted glass, butter paper.
Light gets through, but it gets scattered. It's like the rays get scrambled on the way through. You can see that there is light, like the room gets brighter, but you can't make out the distinct image of what's on the other side. The visual information carried by the light is lost, even if the actual energy gets through.
Okay, this brings us to one of my absolute favorite parts of RM's notes, the pinhole camera.
The camera obscura, a truly ancient device.
RM writes in the margin, I made my own pinhole camera. I just love that. He didn't just read about the theory, he actually built the thing.
It's a rite of passage for a physics student, and it's the absolute perfect demonstration of rectilinear propagation.
So describe the setup for us. The text says you need 2 boxes.
Right. You have a larger cardboard box with a tiny pin-sized hole punched in one side. Then you have a smaller box that slides snugly inside the larger one. The smaller box has a translucent screen, like a piece of tracing paper on the end that faces the pinhole.
So you point the pinhole side at a bright object, maybe like a candle or a tree outside your window. What happens on the screen inside?
You see an image of the object. But, and here's the magic part, it is inverted. It's completely upside down and flipped left to right.
Why upside down? That always confused me as a kid. Why does a tiny hole make things turn upside down?
It's because of those straight lines we were talking about. Imagine light coming from the very top of a tree. To get through the pinhole, which is tiny, that specific ray of light has to travel in a straight line, sloping downwards. So it travels from the top of the tree, through the hole, and hits the bottom of the screen inside the box.
And light from the bottom of the tree?
It travels in a straight line, sloping upwards to get through the hole, so it hits the very top of the screen. The rays cross each other right at the pinhole. It makes the X shape, so the top becomes the bottom, and the bottom becomes the top.
That is such a satisfying explanation. It's pure geometry. No glass lenses, no electronics, no sensors, just straight lines crossing through a hole.
It is elegant. And the text mentions solargraphy, which uses this exact principle to track the sun over long periods of time. Before we had complex glass lenses and digital sensors, this was how we understood imaging. In fact, our own eyes work on a very similar principle, though we do have a lens to help focus. But the actual image projected onto your retina, the back of your eye, is physically upside down.
Wait, really? The image on my retina right now is upside down?
Yes. Physically, the light hitting the back of your eye projects an inverted world.
So why don't I see the world upside down right now?
Because your brain is an incredible supercomputer. It flips the image right side up for you in real time. It processes the raw visual data and corrects the orientation so you can function.
That is wild. Our brain is doing post-production video editing constantly.
Constantly. If you wore special mirrored glasses that flipped your vision upside down, after a few days, your brain would actually adapt and flip the feedback so you saw normal again.
That is incredible. RM also notes that moving the camera changes the image size.
Right. If you slide the smaller box, which is the screen, further back away from the pinhole, the image gets bigger. It's exactly like moving a movie projector screen further away from the projector.
Let's move to segment 5, shadows. The text gives us what they call the recipe for a shadow.
3 mandatory ingredients. You cannot bake a shadow without them. 1, a source of light. 2, an opaque object to block that light. And 3, a screen.
The screen part is interesting to me. We usually take it for granted. The ground, the wall, the sidewalk. But the text says without a screen, the shadow exists in space, but isn't actually visible.
Think about it on a massive scale. If you are floating in deep space and you hold up a baseball in front of the sun, that ball casts a shadow. There's a literal cone of darkness stretching out behind that ball for thousands and thousands of miles.
Right.
But if there is no wall, no planet, no other astronaut to catch that shadow, you don't see it. It's just a region of darkness waiting to be intercepted.
That adds a three-dimensional element to shadows that I usually forget about. We tend to think of shadows as flat, two-dimensional shapes painted on the sidewalk. But they are actually volumes. They are 3D tunnels of darkness.
Exactly. They are physical voids in the light field.
And the text notes some key characteristics of these voids. First, shadows are always black.
Regardless of the object's color, you hold up a bright red ball, the shadow is black. You hold up a neon green ball, the shadow is still black. Because a shadow is the absence of light. It carries absolutely zero color information. It's just a zero signal.
And it has no internal detail, just the pure outline.
Right. It's a silhouette. It tells you the general shape, but not the texture or any of the internal features.
Arm's text also talks about the dynamics of size. This is activity 3. It says, if I move the object closer to the light source, the shadow gets huge.
It's all about the angles of the rays. Bringing the object closer to the light source blocks a much wider angle of the light rays coming out, so the shadow expands massively on the wall. If you move the object away from the light towards the screen, the shadow shrinks back down and becomes much sharper.
That sharpness leads us to two very cool terms that I honestly haven't thought about since high school physics. Umbra and penumbra.
The true anatomy of a shadow.
It sounds like a secret society, the Order of the Umbra.
It does sound a bit mysterious,
Right.
but it's geometrically very simple. The umbra is the heart of the shadow. It's the central darkest part where no light reaches whatsoever. If you were an ant standing in the umbra as a shadow and you look back at the light source, it would be completely 100% blocked. You wouldn't see the bulb at all.
And the penumbra.
That's the fuzzy edge. It's the outer region of the shadow that receives some light, but not all of it. Maybe light from the left side of the light bulb reaches that spot, but light from the right side of the bulb is blocked, so it's a partial shadow. It looks lighter, more grayish.
So if I have a really, really tiny point of light, like a sharp laser pointer, do I get a penumbra?
No. A true point source of light creates a perfectly sharp shadow, only an umbra. You only get a penumbra because most everyday light sources, like the sun or a fluorescent bulb, have physical size. They are extended sources.
That explains why my shadow on the ground on a sunny day is always a bit fuzzy around the head.
Exactly. The sun is huge. Light is coming from the left edge of the sun and the right edge of the sun simultaneously. Your head blocks some of it, but not all of it at the very edges of your shadow. That fuzziness you see is the penumbra.
Now, speaking of giant shadows, segment 6 takes us to the cosmos. Eclipses.
An eclipse is really just a shadow on a planetary scale. It's the exact same physics as the baseball and the flashlight, just much, much bigger.
The text sets the stage here. You need a straight line alignment. The sun, the moon, and the earth all lining up perfectly.
It's called syzygy. The text doesn't use the word, but that's the astronomical term for when three celestial bodies align perfectly like that.
Let's start with the solar eclipse. The text says this happens on a new moon day.
This is the dramatic one. The physical order in space is sun, then moon, then earth. The moon gets exactly in the middle.
So the moon casts a shadow down onto the earth.
Right. And because the moon is vastly smaller than the earth, its shadow doesn't cover the whole planet. It just draws a small, dark, moving circle across the earth's surface. If you are lucky enough to be standing right in the umbra of that shadow, that dark center, you see a total solar eclipse. The sun goes completely black in the middle of the day, the temperature drops, the stars come out.
And if you are in the penumbra,
You see a partial eclipse. It looks like a glowing cookie with a bite taken out of it.
Yeah.
The sun is only partly covered.
Aram has a massive intervention right here in the notes, a really huge safety warning.
Good job, Aram. This is critically important.
He writes in big letters, "Fry your eye."
He's not wrong. It's a vivid description, but medically accurate.
He says never look directly at the sun because the eye won't detect the UV light and it can cause permanent blindness. I want to dig into that. Why won't the eye detect it?
This is a real hidden danger. During a partial eclipse, the sun gets visibly dimmer, right? So your body's natural reflex to look away or squint is suppressed. Your brain thinks it's safe. Your pupil actually dilates.
It opens up.
Yes, it opens up wide to let in more light because it feels dark outside. But the invisible UV radiation is still blasting out at full strength from the exposed parts of the sun. So you're essentially opening the blast doors wide open and inviting high-energy radiation to literally burn the cells of your retina.
And the really scary part is,
You don't even feel it happening. The retina has absolutely no pain receptors. You could be frying your vision irreparably, and not know it until hours later when you realize you have a permanent unfixable blind spot dead in the center of your vision.
That is absolutely terrifying. So fry your eye is exactly what's happening.
It is. ARM suggests using a pinhole camera or special certified eclipse filters. That's the only truly safe way to watch it.
Then we have the lunar eclipse.
The cosmic configuration changes for this one. Now the order is Sun, then Earth, then Moon. The Earth places itself squarely in the middle.
So the Earth casts its giant shadow onto the moon.
Exactly. And because the Earth is so much bigger than the Moon, it can cover the entire Moon in its shadow very easily. This happens on a full moon night.
ARM has a personal note here, too. He says on, I think, the 7th of September 2024 in India, there was a lunar eclipse, which I did take photos of. It was amazing.
I love that he's actively documenting his own observations. He's engaging with the night sky. And the text also mentions the blue blood moon from 2018.
I wanted to ask about that. Why does the moon turn red during a lunar eclipse? The text doesn't go very deep into the mechanics of this, but it calls it the blood moon. If the moon is fully inside the Earth's shadow, in the umbra, shouldn't it be pitch black?
Ah, that is the magic of Earth's atmosphere. The solid bulk of the Earth blocks the direct sunlight, yes. But our atmosphere, the layer of gas around the planet, acts like a giant lens. It bends or refracts some of that sunlight on the edges of the planet.
Okay, but why red?
Because the atmosphere scatters the blue light away. That scattering is actually why our sky looks blue during the day. The shorter blue wavelengths bounce off the gas molecules. The longer red wavelengths, however, pass straight through the atmosphere. So the only light that makes it through the atmospheric lens, bends around the Earth, and hits the moon is that deep red light.
So it's like filtered sunlight.
It's essentially the light of every single sunrise and sunset happening on Earth at that exact moment, projected simultaneously onto the surface of the moon. If you were an astronaut standing in the moon looking back at Earth during a lunar eclipse, you would see a black disk surrounded by a brilliant glowing ring of red fire. That red light is what illuminates the moon.
That is incredibly poetic. A lunar eclipse is literally the reflection of all of Earth's sunsets at once.
It really is. It's one of the most beautiful phenomena in astronomy.
Now let's bounce over to segment 7, reflection.
The bouncing ball analogy.
The text asks you to visualize this. What happens when you throw a tennis ball hard at a solid wall? It bounces back. Light does the exact same thing.
That is reflection in a nutshell. Light strikes a surface and physically changes direction.
It mentions mirrors, obviously. A plane mirror, meaning a flat mirror, reflects most of the light that hits it. But it also mentions water. Still lakes perfectly reflecting trees and hills.
Any sufficiently smooth, polished surface can act as a mirror. The key property is smoothness. If the surface is rough on a microscopic level, like a piece of paper or a cotton shirt, the light rays scatter in a million different random directions. That's why you can see the white paper, but you can't see a reflection of your face in it. The image data is scrambled. But if the surface is perfectly smooth, like glass or still water, the light bounces off in a highly coherent way, keeping the rays aligned and preserving the visual image.
This leads to the final big distinction in the text, and I think this is really helpful for you listening to cement these concepts. The fundamental difference between a shadow and an image.
It's surprisingly easy to mix them up conceptually, but physically they're complete opposites.
Let's break it down using activity 6 from the text. Let's compare them directly. First, the cause.
A shadow is caused by the strict absence of light. It's a physical blockage. An image, like in a mirror, is caused by the presence of light changing direction and coming back to you.
Second, color.
Shadow. Black. Always. It's a void. Image, the exact same color as the object. If you look in a mirror, your bright red shirt is still bright red.
And third, the level of detail.
Shadow. Outline only. Absolutely no internal details, just a boundary shape, image.
Yeah.
Full, rich detail. You can read the logo on your shirt, see the color of your eyes, the texture of your skin.
So a shadow is a void, an image is a copy.
Exactly. One is the subtraction of visual information. The other is the redirection of visual information.
So what does this all mean for us? We've gone on this massive journey from the literal speed of light across the vacuum of space, down to the creation of daily shadows, and up to the grandeur of cosmic eclipses.
It connects us deeply to the physical world. When you finally understand these basic mechanisms, you stop taking vision for granted. You realize that every single time you see a non-luminous object, a book on your desk, a tree outside, the face of a friend, you are actually witnessing a complex, invisible game of quantum billiards, where trillions of photons are bouncing off surfaces and perfectly hitting your retinas.
And without that constant reflection, we'd be totally invisible to each other.
We would. We're all non-luminous bodies. We rely entirely on borrowed light to be seen in this universe.
I keep thinking back to Aram's notes throughout this whole text. He's learning this for the very first time. He's building his own pinhole cameras out of cardboard boxes, taking photos of eclipses from his home in India. It's such a powerful reminder that science is active. It's not just memorizing the definition of rectilinear propagation for a test. It's holding the bent pipe to your eye, moving it, and going, whoa, the light actually stopped.
That is the true scientific spirit. Curiosity, observation, testing the world around you. Aram isn't just passively reading a book. He's actively participating in the physics of the universe.
And that note he made about the speed of light, looking at the sun and realizing it's 8 minutes in the past, it makes me wonder something profound. If we're always seeing the past purely because light takes physical time to travel across space, do we ever truly see the present?
In the strictest physics sense, no, we don't. Even when you look at me sitting right across this table from you, there is a tiny infinitesimal delay. Light takes a fraction of a nanosecond to get from my face to your eye. We are all living in our own little isolated time bubbles, constantly seeing a world that has already happened. The deeper you look into space, the further back in time you see. But even here, in this very room, we are never quite in the exact now.
That is heavy, and a perfect, provocative place to leave it for you to think about.
Indeed.
Thank you for joining us on this deep dive into the fundamental physics of light, featuring the invaluable wisdom of Aram.
It was an absolute pleasure.
Next time you walk outside on a sunny day and see your shadow stretching out on the pavement, take a closer look at it. Find the umbra, look for the penumbra on the edges, and just take a second to remember the cosmic geometry that's making it all happen. Thanks for listening. We'll see you next time.